Chapter 4, Application of Forces. Main focus here is force of friction and its application. Here are key concepts based on a Nelson physics textbook, grade 11 university. After completing this chapter, you'll be able to describe a relationship between mass, gravitational field strength, and force of gravity, analyze and solve problems involving force of gravity and free fall, analyze and solve problems involving friction and coefficient of friction. There's a lot of examples we're going to do this, and conduct an inquiry that applies Newton's law, etc. This is chapter 4, section 1, so section 4.1, gravitational force near the Earth. Some of those concepts that we're going to cover here in this section, you already know from section 1.4, gravitational acceleration near surface of the Earth. So it is a same concept, but seen from a different point of view, from acceleration and from gravitational force and gravitational field point of view. We're going to talk here about air resistance and the cross-sectional area. Air resistance exists, so it will affect the motion. So air resistance is a special form of kinetic friction. And why kinetic? Because it's about motion. So object is moving through air, so then the air resistance will act on that motion against motion. Air resistance depends on a cross-sectional area of the object and its speed. Let's focus on a cross-sectional area first. Let's analyze a piece of paper falling down and compare that with a ball, for example. First, we can see a flat piece of paper and crumbled piece of paper will fall at a different rate. Why? Because they have a different cross-sectional area. Crumbled paper will have a cross-sectional area comparable to the ball. That's why the rate of falling that crumbled paper is comparable to the rate of falling that ball. Now, the flat piece of paper on the left has a larger cross-sectional area, while crumbled piece of paper has smaller. Now, why don't they fall the same, the crumbled paper and that ball? There's another reason. First of all, there's no exactly the same cross-sectional area for both. It looks like crumbled paper has a little bigger cross-sectional area. And the second one that is very, very important is the shape. It's an aerodynamic shape. So ball is smooth. Air has an easy way to pass around, while the random crumbled piece of paper is going to be facing a lot of difficulty to go through air. So that's why manufacturers of airplanes and helicopters and cars and trains that goes through air try to make those products as aerodynamic as possible, as smooth as possible, to be able actually to navigate through air with the least waste of energy. Now let's analyze air resistance and the speed of the object. The only force acting on a skydiver, as is jumping out of a plane or a helicopter in this case, is the force of gravity. And right after starting the fall through air, both force of gravity and air resistance act on a skydiver. So air resistance at the beginning, of course, is weak because of the small speed. The skydiver accelerates initially at 9.8 meters per second squared down, but that acceleration keeps decreasing. As speed increases, the air resistance will increase, while the acceleration will decrease. As a skydiver continues to fall, the acceleration at some point will become zero. So the terminal velocity or terminal speed is reached, which is a constant speed of the falling object. So the object cannot reach any faster speed than a terminal speed. At this point, a dynamic equilibrium is established. What does it mean? That means that F net is zero. So force of air resistance and force of gravity will cancel each other. As a result, acceleration will be zero. As a result, velocity will stay constant. Although air resistance exists, air resistance often is ignored when we solve physics problems, because that makes solving a problem very complicated, very difficult. So most of the time you're going to ignore it, or it is already mentioned that air resistance is negligible. So that means you do not take that into consideration at all. Take a look on the diagram on the right. When an object is under free fall, that means that the only force that is acting on it is a force of gravity. As a result, all the objects will fall at the same rate in absence of air resistance. So when we talk about free fall, we talk about ideal situation when the air resistance is negligible. There's a beautiful, useful video in YouTube from BBC that illustrates falling a feather and a ball in the presence of air resistance and in absence of air resistance. You'll see that in absence of air resistance, they will fall perfectly at the same rate. I recommend it. In 1.6, we talk about gravitational acceleration. Now the gravitational acceleration has a different name, but it is the same thing. Gravitational field strength. So gravity is an action at distance force that pulls an object without making any contact with it. To understand the gravitational field, we should know what a force field is. The force field is a region, is a space. So a region of space surrounding an object that can exert a force on other objects. The field exerts a force only on objects placed within that region that are able to interact with that force. Remember, the range of the gravitational force is infinite. So that means a field is infinite. Gravitational field is infinite. So no matter how weak that field is, there is a force acting on it. More about this you're going to learn in chapter 6 in grade 12. But for now, that is enough. Gravitational field strength is a force per kilogram of mass acting on object within a gravitational field. The symbol is the same thing as a gravitational acceleration, g, and value is the same, but the unit is slightly different, although we did use it on section 3.3, 3.4, 3.5 on a previous chapter. The gravitational field strength is a vector quantity, as acceleration is the same thing. Now, force of field exists and surround the object, especially a massive object like Earth. So to represent the gravitational field around the Earth, we draw field lines that point toward the center of the Earth. As you see, the further away from the surface of the Earth, those lines are further apart. That means that gravitational field strength decreases as you move away and increases as you move closer to a surface of the Earth, or you move closer to a center of the Earth. Now, mathematically, we can determine the gravitational field strength at a particular location. You can measure the force of gravity acting on an object and divide it by mass of the object. So formula is G is equal Fg over m. Now, unit of force is Newton and unit of mass is kilogram. So unit of gravitational field strength is Newton per kilogram, or it is force per unit of mass. So since that Newton is a derived unit, based on second Newton law, now you know that force is equal mass times acceleration. We can write a Newton as a kilogram times meter per second square, which is a unit of acceleration. So now kilogram and kilogram cancel. You see that G unit is a Newton per kilogram or meter per second square. Diagrams on the right are Earth with water, Earth without water. So as you see, Earth is not even close a perfect sphere. It's not a perfect sphere. So as a result, in many different places, location, gravitational field strength has to be different because it's different distance from the center of the Earth. So if you take a look on a diagram on the top right, the diameter, as it measured from pole to pole, is 12,714 kilometers. As it is measured through equator, it's 42 kilometers longer, bigger. So that means that from a center, the radius, or a distance from center of the Earth, is a 21 kilometer difference from poles, center to poles, and from center to equator. As a result, that gravitational field strength has to be different. So it's greater at the poles and is weaker at equator. How this is calculated, more about this, you're going to do that in grade 12, but for now, just to have an idea where this gravitational field strength comes from and why it's different. So if you see that mass of Earth is constant and the radius of the Earth does change, as I mentioned, but in North America, that the radius is approximately at a 6378, so 6,378.1 kilometer. And if you make that calculation, where the G is 6.67 times 10 in power of negative 11, if you do that calculation, the answer will be 9.8 meter per second square. So that's why we use that 9.8 meter per second square as a gravitational field strength or gravitational acceleration in our calculation. That table on the lower left is the values of a gravitational field strength on the poles and equator. You see that there is a slight difference between those two. In everyday language, terms mass and weight are used interchangeable. But these two words have different meaning. They are not the same. While mass is a quantity of matter in object, weight depend on mass but depend on gravitational acceleration as well. The only way to change mass of the object is either to add or remove matter. So weight or a force of gravity are the same thing. The weight of the object depends on location and the magnitude of Earth gravitational field strength, G, or gravitational acceleration. So the weight is equal to the force of gravity is equal to mass times gravitational acceleration or gravitational field strength. So mass is different from weight. On the moon or on another planet, your weight is different, but your mass is the same. For example, the magnitude of gravitational field strength, also force of gravity or weight, on the surface of the moon is approximately 1/6 of that on the Earth's surface. On a diagram on the right, you see a mass 100 kilogram. It is the same on moon surface and on Earth's surface. However, weight on an Earth's surface is 980 Newton, while the weight on moon surface is 162.2 Newton. So mass of the object is the same everywhere. Weight of the object depends on location. Let's analyze the difference between what is the weight and apparent weight. Weight is the force of gravity, but apparent weight, because of the motion, the object appears to have a lighter or heavier weight. Now let's see what is a normal, what is a weight. As you stand on a bathroom scale, the magnitude of normal force is equal to force of gravity. Because you are not moving, that means the F net is 0. Based on a first Newton law, this would be the same if you are moving at a constant velocity, or as I said before, not moving at all. So F net is 0, and those two forces, normal force and force of gravity, has to cancel each other, so they must have the same magnitude. So if an elevator is not accelerating, so it's staying at rest or moving at constant velocity, we know that weight is exactly your force of gravity. You already have experienced apparent weight, so that means you are feeling heavier or lighter if you ride a roller coaster or if you ride the elevator. So if an elevator accelerated upward, then you see that you feel heavier because normal force not only has to fight the gravity, but has to accelerate you upward. While the elevator is accelerating downward, then normal force have an easy way accelerating you downward because the gravity is helping you. Let's say that you're free falling. So elevator or any way, you are falling at a rate of acceleration. So you are accelerating downward at 9.8 meters per second. As a result, you and the scale are falling at the same rate. So the scale, nothing is holding scale, so the scale is not holding you in order for the normal force to exist. As a result, normal force will not exist, it's going to be 0. As a result, the reading on a scale is going to be 0, then you're going to feel weightless. Let's illustrate the apparent weight with an example. A student with a mass of 55 kilograms stands in an elevator that accelerates. Determine the student's apparent weight, or a normal force, during each acceleration. A. Elevator accelerates upward at 2 meters per second square. We draw a free body diagram. So Fg and Fn is moving upward, so that is acceleration is up, and positive direction has to be up. So it's a y-axis is accelerating, so that means F net y is equal to ma. Then F net y is equal to sum of all forces, we have just 2, is equal to ma. And now since that we have positive up, Fn is positive, Fg is negative. So we solve for Fn, we move Fg to another side of the equation, becomes positive. So Fg plus ma. So Fg is mg plus ma, we factor m. It is g plus a. And then you plug numbers there, 55 kilogram times 9.8 plus 2 meter per second square. So the answer will be 649 Newton. Now, let's say that elevator is accelerating downward. Same rate, just for simplicity. We draw a free body diagram. Now it's moving up, moving downward. So the down is positive direction, which is the direction of the acceleration. And we do the same thing, similar to up. The only thing you have to pay attention to a sign, which is down. So F net y is ma because it's accelerating, and F net y is equal to sum of all forces, is the same thing. Now we have to follow positive direction, which is down. So Fg is positive and Fn is negative, is equal to ma. We can solve for Fn, which is Fg minus ma. So Fg is mg minus ma. We factor m, g minus a. Then we can plug numbers. 55 kilogram times 9.8 minus 2, that is 429. If you take a look, the acceleration upward, you feel heavier, and acceleration downward, you feel lighter than normal. But what is normal? A student normal weight is when there is no acceleration, when F net is 0, when the forces are balanced. So that means, based on the first Newton law, the student is moving at constant velocity or not moving at all. So to solve it, as always, we draw a free body diagram. We have two forces, Fg and Fn. Since that is in equilibrium, we just keep it traditional, positive up. Then we apply first Newton law, not second, first Newton law, because F net is 0. So F net y is equal to 0. That means sum of all forces is equal to 0. So Fn and Fg has to be 0. Then we follow the positive direction, even in first Newton law. So if we follow the same steps, we will never make mistake. So Fn is positive, Fg is negative, is equal to 0. So then we move Fg to another side of the equation, becomes positive. And we know that Fg is equal to mg, and we have m and we have g. So we plug those numbers and find the Fn is 539 Newton. So that is a normal weight. That is a force of gravity without acceleration. Okay, so next one, what will happen if the student will free fall? Let's see. We draw a free body diagram as always. So we have two forces, Fg and Fn, and acceleration is going downward. That will be a positive direction. So we follow the same step. Fny is equal to ma. Why? Because it's accelerating. It's a second Newton law this time. So F net y is equal to Fn plus Fg. Those are two forces. Is equal to ma. Again, we follow the positive direction. Is down this time. So Fg is positive. Fn is negative. Is equal to ma. And acceleration is always positive. We keep it that way to make it easier and not confusing. And Fn is equal to Fg minus ma. We know Fg is mg minus ma. And we can factor m, and what is left there is a g minus a. Then we plug numbers. Thing is that g is 9.8 and a is 9.8. So it's 0. 0 times 55 is 0. So that means the normal force is 0. So although we draw, and we did the right thing to draw a normal force, in a free fall there's no normal force because nothing is holding anything. Everything is falling at the same rate. So that's why it's exactly what we actually mentioned before. There's no reading on a bathroom scale because, or no tension on an elevator cable, or no normal force on a bathroom scale holding you, or a elevator floor holding you, because everything is falling at the same rate. So that means nothing is holding. Microgravity and free fall. In grade 12, after studying uniform circular motion and orbits, you're going to have a better understanding of this concept. However, for now, we can say the astronauts that you might have seen through video clips from NASA documentaries. Astronauts appear to float within that International Space Station, although value of G at that level is 8.7 meters per second square. So somebody might ask why 8.7 and not 9.8 as we usually use in North America, because it's further away from the center of the Earth. So this floating thing is referred as weightlessness or microgravity. So the force of gravity still acts on astronauts as they are being pulled toward the Earth's center. But International Space Station with astronauts and all things around are in constant free fall. So that means that force of gravity, although it's a little bit weaker compared to the force of gravity that would be on that Earth surface, it's still acting on them. But free fall, as we actually mentioned on the previous examples, there is no normal force holding it. There is nothing stationary. So everything, all as a complex, as all International Space Station, are falling down. The same thing happened to a moon. Although it's orbiting the Earth, it is in a constant free fall. More about it in grade 12. So that's a practice for you. Try rope A is tied to a block 1 and rope B is attached to both block 1 and 2. The mass of block 1 is 4.2 and block 2 is 2.6. You leave both blocks straight up. Calculate the tension in a rope when the blocks move at a constant velocity. So that means there's no acceleration. And when it accelerates at 1.2 meters per second up. So that's for you to try to solve apparent weight problems. So now instead of Fn as a normal force, you're looking for tension, which is pretty much the same formulas, just tension instead of Fn.